Welcome all. So, this is the continuation of our previous lecture, which is on pore water pressure parameters. We have already seen Skempton's pore pressure parameter, which corresponds to a triaxial condition. In this lecture, we will see a different way of presenting the pore water pressure parameter and what is known as overall pore pressure parameter B. So, we will start with the lecture, which is overall pore water pressure parameter B bar. There are different ways by which pore water pressure equation can be expressed. Now, before going to B bar, we will see a typical representation of pore water pressure equation. This is what we have already seen, we have understood. This can be written in this manner, where delta U is equal to B into 1 by 3 delta sigma 1 plus 2 delta sigma 3 plus 3 A minus 1 by 3 into delta sigma 1 minus delta sigma 3. This we all know, it is deviator stress Q, which we have seen in the previous lecture. What is this? Delta sigma 1 plus 2 delta sigma 3 by 3. This is nothing but the mean stress for triaxial condition. Now, we need to understand that we have seen it in terms of P dash, but here it is P. This is a total stress condition. So, mean stress, this is mean stress P, and this is deviator stress Q. So, the Skempton's pore pressure equation can be rewritten in this manner to express it in terms of mean stress and deviator stress. So, if you expand this, you will get the same equation. So, this is mean total stress delta sigma 1 plus 2 delta sigma 3 by 3. Now, if soil behaves elastically, we know that A is equal to 1 by 3. So, if you substitute it here, then this becomes 0. So, pore pressure depends solely on the mean principal stress, only in those circumstances where the soil behaves elastically. Deviator stress is there is no contribution from deviator stress. Now, for all those conditions where A is not equal to 1 by 3, deviator stress has significant influence on delta U. Now, let us see what is overall pore pressure parameter B bar, which relates delta U with only delta sigma 1. Delta sigma 1 is normally considered in terms of loading. So, what is the total stress which is acting because of some load, external load acting on the soil. So, Bishop in 1954, in this again a classical paper which deals with pore pressure coefficients, the use of pore pressure coefficients in practice, which is published in Geotechnique. The relationship, this B bar, this relationship is useful while dealing with practical geotechnical problems. Knowledge of initial delta U as a result of loading is necessary to estimate the stability of foundation soil of an earth dam. Maybe for a drained condition after a pretty long time, what will be the kind of state of the soil? For that, we need to know what will be the kind of pore water pressure that gets developed due to loading, which is very essential for situations like foundation of soil of an earth dam. Stability and settlement of impervious fill of earth dam due to superimposed layer in staged construction. Increase in stress due to rapid drawdown. It is not only that you are adding water to it, but when there is immediate release of water from the soil, the effective stress increases. Now, due to this effective stress increase, there will be a kind of settlement. So, that issue is relevant with rapid drawdown. Now, pore pressure change due to removal of weight from overlying soil. So, what will be the pore pressure change due to release? That is, we are removing the weight. So, what happens during that time to pore water pressure? Again, we start with the same equation, Skempton's equation. We are doing again some mathematical rearrangement. B into, we are adding and subtracting delta sigma 1. So, delta sigma 1 minus delta sigma 1 plus the remaining equation. So, this can be rewritten as delta sigma 1 minus delta sigma 1 minus delta sigma 3. You are just taking minus outside plus this. So, you can write delta u is equal to b into delta sigma 1. So, from here when you can take delta sigma 1 minus delta sigma 3 outside, that will give you minus 1 minus a delta sigma 1 minus delta sigma 3. So, again you can take delta sigma 1 outside. So, when you take delta sigma 1 outside, here it will become 1 and here it will become 1 minus delta sigma 3 by delta sigma 1. So, delta u by delta sigma 1 is equal to b into 1 minus a 1 minus delta sigma 3 by delta sigma 1. So, this overall pore pressure parameter B bar is this particular expression, which is b into 1 minus a 1 minus delta sigma 3 by delta sigma 1. So, this is the overall pore pressure parameter equation B bar. Now, delta u by delta sigma 1 is a function of B bar. So, once you know B bar, we can always calculate what will happen to delta u as a function of delta sigma 1. For that, to explain this, let us take an example of an earth embankment which is shown here. Now, there is a soil element here which is at a depth of h. Okay. So, assume this delta sigma 1, it is not assume, delta sigma 1 is very much equal to gamma into h, where gamma is the unit weight of soil. Now, what we are assuming is that the for above equation delta u by delta sigma 1 is equal to B bar makes it convenient to determine the variation of pore water pressure with increase in height of the embankment during staged construction. Now, what we are assuming is that the entire loading and the influence that is happening at this particular point is due to the major principal stress delta sigma 1. So, delta sigma 1, so whatever is the change that is happening at this point is entirely due to its geostatic stress, which is gamma h, and that is true also because there is no load acting. Whatever is the superimposed load which is acting at this particular point, that can be assumed as the major principal stress delta sigma 1, which means to say any kind of loading is represented here in terms of delta sigma 1. So, this assumption is important because then only you can determine the pore water pressure as a function of delta sigma 1. So, we are not concerned about other principal stresses here, we are correlating or we are assuming whatever stress change happens, that is delta sigma 1 only. So, once we know that, then the above equation, this particular equation, it makes it very convenient to determine the variation of pore water pressure happening with loading. Loading means increase in height of the embankment during stage construction. So, that is the beauty of this particular equation. Pore water pressure at any instant of loading, that means staged construction, can be determined. Now, but we have seen that in this particular equation, delta u also is a function of stress ratio delta sigma 3 by delta sigma 1. So, that also becomes important. So, delta u also depends upon the principal stress ratio. Now, we know coefficient of lateral earth pressure K is equal to delta sigma 3 dash by delta sigma 1 dash. So, this is known to us. So, K is equal to delta sigma 3 minus delta u upon delta sigma 1 minus delta u, just transferring this to total stress condition. K into delta sigma 1 minus K into delta u is equal to delta sigma 3 minus delta u. Again you can write, you can take delta u on this side. So, that will give you K into delta sigma 1 plus delta u 1 minus K delta sigma 3. So, K plus dividing it by delta sigma 1, we can get K plus delta u by delta sigma 1 1 minus K is equal to delta sigma 3 by delta sigma 1. Now, this is the stress ratio. We can substitute this in the previous expression. So, if you substitute this for delta sigma 3 by delta sigma 1, the equation takes the forms like this. So, you are substituting it here. Then we again take delta U from this side to this side. So, that will give you 1 minus B into 1 minus A 1 minus K is equal to B into 1 minus A into 1 minus K. So, again we get the expression in terms of delta U by delta sigma 1, but instead of stress ratio, now this is in terms of coefficient of lateral earth pressure. So, B into 1 minus A 1 minus K by 1 minus B into 1 minus A 1 minus K. So, again it is the same overall pore pressure parameter, but in a different form in terms of coefficient of lateral earth pressure. So, in the embankment problem, if the horizontal layers are of infinite extent, it is reasonable to assume that the lateral deformation is negligible. If the lateral deformation is negligible, then we can always say this coefficient of earth pressure K is equal to coefficient of lateral earth pressure at rest, which is K naught. And B bar can be determined from laboratory test by maintaining the appropriate constant ratio K is equal to delta sigma 3 dash by delta sigma 1 dash, which basically simulates the field condition. So, one thing is if it is of infinite extent, then it can be treated as K naught or any other value of K which resembles the field condition. Now, if the slope is steep and in a condition of limit equilibrium, that is almost the failure condition, then K will take a minimum value and which is close to active condition, which is denoted as Kf. So, that Kf can also be simulated. Now, for any slope with factor of safety which is greater than 1, which is not at failure, K value will be in between these two bounds, that is in between Kf and K naught. So, once we know the appropriate K value, that can be put into this particular equation, and that gives us what will be the pore water pressure for any change in loading. So, the summary of overall pore pressure parameter is the use of this parameter B bar. It is a convenient way of estimating pore water pressure as a function of loading in a practical situation. Delta U depends on delta sigma 1 and the principal stress ratio delta sigma 3 upon delta sigma 1. B bar is expressed in terms of coefficient of lateral earth pressure, which comes from this. If soil behaves elastically, A is equal to 1 by 3, then delta U will depend only on the mean principal stress. For not equal to 1 by 3, then deviated stress part has a significant influence on delta U. So, that is all for today's discussion on pore water pressure. There is one more section left to be discussed in this, which we will see in the next lecture. Thank you.